Afternoon, Caleb Eckhardt is going to be talking to us about stability, residual finiteness, and lots of examples.
All right, Larry. Thanks for introducing me. Thanks for coming. So that's the title of my talk. Let me find it. All right, so I don't have to re-say the definition of Hilbert-Schmidt stability. That'll be the main topic is Hilbert-Schmidt stability, some connection to permutation stability. So I'll skip the definitions, but I'll remind you of some key points that will come up during my talk. Okay, so for starters, most of the groups will be amenable. And so this is a reminder from earlier talks. So everything underneath this line is amenable. Stable, this is the same as flexibly Hilbert-Schmidt stable. For amenable, I believe that this is unknown in general if these are the same. Okay. And that's the picture for flexibly Hilbert-Schmidt stable. You're allowed to expand just a little bit when you're defining your homomorphisms. Right? But the L2 norm has to still be the same. And now this implies maximally almost periodic, which just means you have a separating family of finite dimensional representations, not necessarily finite representations. The main examples I'm interested in are all finitely presented groups, but they're built up from non-finitely generated groups. So I'm interested in also throwing the word map in there as opposed to just residually finite. So if you don't like that word, then just for finitely generated, this is residually finite. Okay, so just separating family of finite dimensional representations. And then this is the same as very flexibly. Flexibly Hilbert-Schmidt. And the picture is this. So we can expand it as much as you want, but when you cut down to this corner, they have to be the same on the L2. Right up here, that's taken care of because this is small, but when you cut down, close on the L2. Okay, so that's the difference. Here, just for amenable. Ignore the numbers, that's just for me. That's what I want to do. All right, now let's look at the dynamic picture of this. Picture of just what I wrote up there. So by dynamic, I mean you have, say, a abelian group and a single automorphism acting on it. Okay, so abelian group, single automorphism. Z, so that's abelian. All right, so I'm going to rewrite some of these words. So here you get a classic dynamical system. So the transpose gives you the dual map over here. And in this case, Hilbert-Schmidt stable is the same as dense periodic measures. So Itamar define that, I'll say it again. Just means you have dense periodic measures. It means look at your invariant measures with finite support, close that in the weak star topology, and that's every invariant measure. Okay. Dense periodic measures. And then I'm going to flip out a map for residually finite. So here, residually finite. And that's dense periodic. Okay, either of these are easy to see. Let's say it's finitely generated. It should be fine.
Right, what does dense periodic points mean?
Compared
to dense periodic measures?
So dense periodic points means the set of periodic points is dense.
In the points.
That's it. Yeah, so just as it sounds.
Okay.
Okay, there's a night. really want to save the middle word. All right, I'll put this up here, but then I'll put it back up. I'll just use the other side. And up over here. Okay, so connected to this is a nice theorem, recent theorem by Yari. So these are actually the same. So these are equivalents for finitely generated groups. I can just write it fully in case it's on the job market. So Gates-Moore also mentioned this result, but it bears repeating that when a semi-direct product with Z, when the entire group is finitely generated, not necessarily just A, when the entire group is finitely generated, then those two notions say what I wrote over there is true. Then finitely generated, and residually finite if and only if Hilbert-Schmidt stable. Okay, I believe that even in the case where A was finitely generated, this wasn't known in full generality until this result. So even when just A was finitely generated, this was unknown. So it's a nice result. And roughly, eventually, what I'll get to the point is that these notions are different for general finitely presented groups. Okay, these notions are different for finitely presented groups, but in this case, the classic dynamical setting, they're the same for finitely generated. I meant to write introduction over here also. Okay, that's for me, not really for you. But that was the introduction. And thus begins my talk formally. And this is the jumping off point. Okay, so this is the lead in to part one. Which will be about very non-finitely presented groups, but from these very non-finitely presented groups, we'll build up some very finitely presented groups. That's the key, but this is kind of the jumping off point. All right, and this part I'm going to slow down. The opposite of the previous talk, which was very high level, this will be as low level. I will win the award for the lowest level talk. That's my goal. All right, so I need the big one for this. There's no way I was going to fly to England and not make a Dickens reference. Okay, so the first one is this. And I'll tell you explicitly what the action. So P is just some fixed prime. Keep it as 2 if you like. And I also have specific matrix representation of this. Okay, so just Heisenberg group over this ring. That's group number 1. Group number 2, very similar. But here it's just Z. Okay, so Z is the acting. So here the action here comes from this is this. So conjugation by this determines the action up here. Still, my asterisks are anything, but now I restrict this coordinate. M is an integer. Okay, so I just restrict here, but the action is the same conjugation by this. So one of these groups is Hilbert-Schmidt stable, and one of these groups is not Hilbert-Schmidt stable.
Yes, or?
Yes, you should, yes, yeah. Vote. Who votes this is Hilbert-Schmidt stable? There's going to be like 90% abstentions. Who votes this is Hilbert-Schmidt stable? Okay, controversy. All right, we'll see who wins. Okay, so this one is Hilbert-Schmidt stable. And this one is not Hilbert-Schmidt stable. But I think it is a subtle distinction, because if you're me and 2 days ago you were writing this up, you re-looked at the proof of this and you realized it has to be robust enough to cover this. So I thought for sure this proof works for that. So Tatiana and I worked on this one. And so I thought, I almost emailed you, said, oh, we totally made a mistake. And then I said, no, maybe in this paper I made a mistake. I eventually realized the tiny difference that I was missing. Okay, so that's what I want to point out first, is just the subtle difference between why one is and why one isn't. And neither are very difficult. This is a stepping stone to what we're really interested in, and this also is a stepping stone to what I'm really interested in. Okay, so neither of these are finitely generated, but I'm really interested in using these to leapfrog into other examples, or to leverage these. That's the new corporate word that is infested mathematics, to leverage these to more interesting examples. All right, but first I want to focus on this one, why this is Hilbert-Schmidt stable. So why? So Tatiana and I were interested in finding an example of a Hilbert-Schmidt stable finitely generated group that is not permutation stable. And this was a step to get there. But for this one, it's pretty easy. Okay, so here we used Hadwin and Sean. So by now we're familiar with the result that for amenable groups, Hilbert-Schmidt stability is the same as if I can approximate my characters by finite dimensional characters. Right? So if I can approximate characters by finite dimensional ones. So we use two results here. One is that if G is virtually abelian, all characters are, let's just say, finite dimensional approximable. Okay, so that just means all characters can be approximated through finite dimensional traces. Okay, so this is step one. Step two is that for any group and any character, if it vanishes outside of the center, so Z of G, I just mean the center of G. So for all elements outside of the center, I get 0. And there's no conditions. I mean, G just has to be residually finite and amenable. Okay, and this is a theme in Hilbert-Schmidt stability. If your character vanished on large parts of your group, we have a much better chance of actually approximating it, right? So this is great. If you have a lot of zeros, it makes life a lot easier. All right, so for this example, we basically cut it down to either this case happens or this case happens. But I really want to focus on number 2 because that's the subtlety that has divided the room, right? Between which one is Hilbert-Schmidt stable and which one isn't. So if we really focus on this, we'll see exactly what's happening algebraically that screws up over here. So we'll spend 2 or 3 minutes actually writing down the two-line proof. So now we're back to that one. Let's call this something. A.
In number 2, you should assume that a group is residually finite.
And residually finite, yeah, okay. Okay, so G has to be residually finite here for it to work, otherwise we're going to some problems. Okay, so proof. 2 lines. It's a workshop, so I'm allowed to do 2-line proofs. So proof. So say phi is extreme trace. AP. Some people, when they say character, they mean extreme. Some people, when they say character, they don't mean extreme. I mean extreme. Okay, so extreme point in the unit sphere. So what that means, I restrict phi to the center, it has to be multiplicative. In particular, it takes values in the circle group. Phi restricted. He is, it can't be 0. T, I just mean the circle group. All right, now, so yeah, this part I'm not even going to touch. So now if I take something outside of the center, I want to show that I apply phi to it, I get 0. That's the key here. Oh, I guess I have some room. So I take G outside of the center. Because I wrote notes. Okay, so K of phi are all the elements of the group that give back to 1. Right, so phi is a trace, so this is a normal subgroup, so just everywhere where this trace is trivial. So everything that gets set to 1. So suppose I take K of phi and I intersect the center and its center. Okay, so the center, you can't tell, is this node right here. Right? So if you have 0, 0, and anything in there, that's your center. So suppose it's cyclic, suppose it's just the integers. It doesn't matter which cyclic subgroup you choose. Okay, and here's the key that divides the two. I'm going to write it. This. There's a lot there. I'm going to stop and talk about it. So there's two class nilpotent groups. When I take any commutators, I'm back in the center. Right? So that always happens. So the key here is that if I take anything outside of the center, I can always locate some h in G so that the commutator has to be back in the center, but it's outside of this cyclic subgroup. Okay? But it's outside of this cyclic subgroup. Okay, and then from this, it's very easy to see that phi of G is equal to 0. Then, if you believe this, okay, so dealing with traces, commutators always show up. But since G commutated with H is in the center, this just pulls out. And so we get phi of G is 0. And so this is in the center, but phi is multiplicative on the center, so this just pulls out. And so phi of G, the only choice is 0. So phi of Z is 0, because this is in the circle group, which is not 0. And again, when you just look at it, it's believable that this same proof should work for this group up here. But I put a pink star by the box that doesn't translate over from one side of the board to the other. Okay, so this is the property that doesn't carry over to this, and let me show you why. If you go to the middle.
Sir, could you explain again why this property does hold in this case, just to make
You'll see it after I write something down.
Okay.
You'll see exactly right. When I write something down, you'll see exactly right. So I'm just going to put something there and then move this back up. Okay, so let's say I take something like this. 1, 1, 1, x, 0, 0. This is G. And H is anything. 1, 1, 1, A, B, C. This is H. When we take commutators, you're really taking products along off diagonal. So I take this commutator. Of course, we have to be in the center. That's fill in. Everything in my commutator start with G inverse, so I get minus Bx. Okay, so I take something like here, and I commutate it with this, I'm just x times b. So now in this case, you give me something, let's say it looks exactly like G, that's general enough. I can find an H I guess H is my B down there. I just take B, P to the minus 25 billion, and you're going to find something outside of the integers. Okay, so there you can always do it. So from that, this check. But now if we come over to the second group, my B value is constrained to be just the integers. Right? My B value is just the integers. So now for this group, GH, let's say the G is just to make things more concrete. 1, 0, 0. And H is anything in there? M. Okay, then when I take the commutator, minus M. So you can only get integers up here. So you can never get things outside of the integers. So again, this doesn't show that this is not Hilbert-Schmidt stable. It just shows that the old proof is not robust enough for the new proof. So all this says, old proof doesn't work. Not necessarily that it's not Hilbert-Schmidt stable.
And how do you know that group is cyclic? That intersection?
No, I don't. Right. So here I have to cover. Yeah. So good point. If it's not cyclic, we're in case 1.
Ah.
Okay. So if it's not cyclic, then it gets big, and the quotient is finite in the center, and so you have virtually annihilated.
Okay.
Yeah, good point. So if it's not cyclic, then case 1 takes care of it. Case 2 is just when it's cyclic. Okay. So yeah. So now let's see why this is not Hilbert-Schmidt stable.
So you're claiming that this example on the left, so it's not Hilbert-Schmidt stable, but it is permutation stable?
No, this one is Hilbert-Schmidt stable.
Ah, sorry, yeah, and
Yeah.
it's not permutation stable?
I don't think so, but we'll get a finitely generated
Oh.
example. Yeah. So yeah. So for those, I want to make sure I get them finitely generated, so they don't feel cheap, you know. Okay, this is also low level. This part of the talk, seeing why this is not Hilbert-Schmidt stable. This is called proposition. So that group is not. And all proofs I know are you anything with Hilbert-Schmidt stability, at least for immutable groups, I have to understand what the characters look like. I don't know any way to do it without actually having an idea of what the characters look like. And so that's basically what I have to do here, is see what all of the characters look like, and then just, since this doesn't satisfy this rectangle, promote this idea over to the character idea. Okay, then done. Okay, so this is one step, or 2 steps. 1, locate the characters. Not finite dimensional characters. So I just have to show it's not Hilbert-Schmidt stable. So if I can locate all of the finite dimensional characters and then produce one bad one, put those together, and everything's okay. So locate the finite dimensional characters. But for me, this means extreme traces. All right, but this is a nice classical dynamical system. So the finite dimensional characters, I just need to know the irreducible representations of this group. But this corresponds to the, I just wrote it, periodic points of the dual space, or the dual action. Right? So now I get this classical dynamical system. If I can locate the periodic points, then I know all of the irreducible representations up to some character scaling of z. Okay, so then I can write them all down. But this action is explicit enough that you can just write them down and see what they are. Okay, so I'll just tell you what the traces look like. So my point of telling you that is that this remains very low level, just like that was. So for any finite dimensional character, our n will be the dimension of the irreducible representation. 2 characters, multiplicative characters. here, and then an extra one just for window dressing, which doesn't really do anything. Let's call this tau. And I'm going to decompose this group as a tuple. A, B, C. Okay, so C is the acting automorphism, A and B are the elements of Z of 1p squared. And maybe I can write this from memory. So tau of A, B, C. So we cut into two cases. Phi of C is 0. And two things have to happen here. If chi1 of B is 1, and n divides C. And then 0 every other way. Pretty sure that's it. Let me just double check. Yep. All right, so once I know all these, and I know this rectangle, and if there's a pink star by it, it tells me the sort of traces I should look for. Anything with cyclic quotient here, right? So I take the easiest possible thing I can think of, which has a cyclic quotient. Let me go over here. All right, so my trace will just be, I'll just crush out the z squared part over there and make it 0 outside. So our trace, so we define phi to be, here I just mean the characteristic function on n, where n is z squared sitting inside of there. All right, so now let's go back to this first board. Why couldn't I have done this for the first group? Just excuse so I can take off my hat sweater. So what goes wrong if I try to do the same trace in the first group? So this is only a positive definite function in the first group, right? It's not a trace. So here, n is a normal subgroup of this. So this is a trace. In the first group, right, if I took z squared, this is just a positive definite function, but it's not a trace. Okay? So if you try to take this proof and work it over here, that's the obstruction there. Okay, so this is a trace. A character. Since n is normal in here. Let's see.
Is the quotient by n residually finite?
No, no. That's key factor that yeah. So definitely not, because once you quotient out by z, you have z of 1 over p mod z, which has no finite homomorphisms at all. Forget about separating. You have no finite homomorphisms. Yeah, so definitely the quotient is not residually finite. So let me just say that now. In fact, if I take pi, let's say z of 1 over p to f, where f is finite. If 1 is in the kernel, then the only possibility is the trivial homomorphism. Right? So once you kill 1, you kill the entire group, where f is finite. So pi of 1 is 1. Okay, so we'll use that here. That's phi. Okay, so the claim is that that's the bad trace. writing down, shifting chalk from this to over there. I know what all the finite dimensional representations look like. So if I look at, say, t of 0, 1, 0, this is 1. So if I can approximate it by finite dimensional representations, then it's some convex combination of these types of characters, which means I'm not going to have any of these types going on. Right? Everything's going to come from the top layer. Okay? Up to some epsilon, but I can just throw off all of these. So basically, everything has to come from the top layer. Tau sub n converge to phi, then they're all in the top layer. They all come from the top layer. So basically what that means is chi1 of b, which is 1, has to be 1. Right? So chi1, oh, I forgot a key part, sorry. Chi1 has finite order. That's otherwise it doesn't work. That has order n. And the first one has to have finite order. And that just comes from looking at the periodic points and writing down what it means. And this is exactly what it means. There's nothing hidden. You just write down what it means to be periodic. But for each one of these, then we need chi1 of 1 equals 1. But that means that all of chi1 must vanish. Right? Chi1 has to be trivial all the way through z of 1 over p. Right, so in the top one, so this has to be 1. But that means chi1, the entire thing is trivial. So that means tau of 1, 0, 0, or sorry, tau of a, 0, 0 for all a have to be 1 as well. So it can't separate z from the rest of the group. So narrow those chi1, but then because chi1 has finite order, this is a homomorphism to a finite group. Right? This is a homomorphism to a finite group. So then chi1 is trivial. So that means that phi of a okay, so now we bring it back to this, and so everything in this first component has to go away. Right? So that means that we can't approximate that. All right, before I move on to embedding both of these groups into finitely generated / presented groups, I want to say there's something more going on here about the bad homomorphisms. And that bad thing sort of promotes to the other examples I'll look at. So it's good to note it on the ground level. So since I'm proving instability, I don't really need the full Hadwin-Shulman theorem. I just have to produce a bad representation. We're done. Right? So here I can produce specifically the bad representation. It comes directly from the GNS representation of the trace. So now we get explicit approximate because the approximate homomorphism that I give you, if it can be perturbed, that means precisely that I can approximate that trace by finite dimensional traces. Okay, so you just quotient out by n, and what's left is an amenable group. And so you can always get an approximate representation there where the trace is just the canonical trace on the quotient. So here it is. I take G. I call it A. This is G. To G mod n, and then I take forms of G mod n. Whatever you want that to look like. Whereas you just take Fuller sequences, act on that, and then these are representations up to some L2 correction. Okay, and these, if these could be approximated, then this trace could be approximated with finite dimensional traces. Okay, so again, explicitly get it if you have a Fuller sequence. But in this case, we can actually do more. I can get an approximate representation in the operator norm that can't be perturbed in the Hilbert-Schmidt norm. But in this case, this is purely dynamics. So in this case, we can get, so just Fulmer, so that means approximate in the Hilbert-Schmidt norm. But in this case, we can get in the operator norm. Just stronger than that. That can't be perturbed in the Hilbert-Schmidt norm. Okay, reminds me of something that Alan was saying in his talk. So in this case, because of how simple it is, so notice it's just a classical dynamical system. So I look at this group, quotiented out by n. I get something that's definitely not residually finite. So dynamically, that means the periodic points are definitely not dense. Z squared half Z. Okay, so this is not a residually finite group, so the periodic points are not dense. But I do get recursion. It was a recurrence, not recursion, right? So there are densely many points that if I start following it, I come back close to where I started. Okay, so from this, I can get approximate operator norm representations. And all you do is you take a point, you follow it until you're close, put that on the diagonal, and then let the action do its thing and just cyclically shift things. Okay, so here, periodic points are not dense, but recurrent points are. And you can even go weaker than that. You can do so-called chain recurrence, which is all you need. But here, I actually get recurrent points. But recurrent points. Okay, and in operator algebraic terms, that just says that this is a quasi-diagonal C-star algebra, which is how I think about everything, but you don't need to for this. Or you can get norm in the approximate homomorphism, but can't be perturbed to the Hilbert-Schmidt norm. All right, so before I do the last examples, let me take this idea and squeeze as much juice out of it as I can.
So yeah, so this is very explicit, so very elementary, but just to understand the generality, could you have just used that amenable groups are MF?
Yeah, but that's
I know.
yeah, I mean, but this is the proof that they're MF. This is exactly the proof that they're MF.
I see.
For this specific group, this is the proof. Yeah.
You had to use the fact that this representation came from a quotient group, right, and not just some tracial representation of G. Because that, do you know that any? It's not known that any tracial representation of G is MF. Like you need that G mod. It's G mod.
You know, it depends. It depends on the trace. It depends on the trace because I mean, probably depends on the trace. Depends on if it satisfies the UCT or not. So in this case, it does satisfy the UCT. This C-star algebra with the canonical trace does, but there's some k-homological things going on, so you can't guarantee it all the time, unless Rufus has proved UCT in the meantime. Okay, still. Okay, so just with this, once we start embedding things, it's easy to see what needs to be kept track of to build more non-examples from this one example. Okay, so 1. I know this 1 doesn't mean anything, but I just have to write it. So 1, let's say I take this picture, this G, and I embed it into a bigger group so that N remains normal. All of G doesn't have to stay normal, but N has to remain normal. Then the obstruction persists. So let's say I have H. I have N. So this embeds, let's call it iota. So iota of N is normal in H. Okay, G doesn't have to be normal, just H has to be normal. 1.1. So if H mod I of N is hyperlinear, right, iota of N, then H is not Hilbert-Schmidt stable, right? Basically the exact same proof. So you can use the exact same representation, but instead of these Fulmers, you use the approximate representations that come from hyperlinearity. Okay, so these are just depicted in there. But you can't do this stuff if it's just hyperlinear. But if it's amenable, 1.2, is amenable, then you can do the same thing. There is just all that stuff, basically. An operator norm. That can't be Hilbert-Schmidt perturbed. Okay, but this is very explicit, so I can just write down exactly what it was. In this case, it's not explicit, so I need some high-powered machinery. So for 1.2, I need a Decreases-White-Winner theorem, or a piece of it which says that traces are canonical trace. So it says more than this, but this is key corollary. Canonical trace on this C-star algebra where H is any amenable group is quasi-diagonal. I guess that's just A. That's all I need to do. Okay, so here I do explicitly construct them, but in general it's difficult or impossible to explicitly construct them. So using this theorem, we can get operator norm approximations that can't be perturbed to Hilbert-Schmidt. Can't be Hilbert-Schmidt perturbed to true representations. And again, Alan's question, he said, what about any trace? Here I'm using a special fact about this special trace. We know, and it follows by work of Hickson and Kasparov, that this satisfies the UCD, which I won't describe or say anything more about, but there's something extra going on in the background that prohibits us from extending this to just any old trace. Okay, so there's something special about this trace. All right. It might work for all traces, but we don't know if it works for all traces. 90% sure that's all I wanted to say for that part. All right, so now back to part 2, the end. I don't have slides to tell you that I'm almost done, but I'm almost done. All right, so if I had 3 boards, I would have kept the initial ones up. So let's get back to these groups here. So this is not finitely generated, but there's an easy way to embed it into something finitely generated. Stick an extra action on. Just hold it. Okay, so let's say that alpha does this, A, B, C. Cuts this in half and it doubles, or sorry, multiplies this by P and divides this by P, so P is the unit here, so that's fine. A over P, P, B. Okay, so that's the automorphism. As we saw with that example, commutators are basically just products, so that's how you recover everything here. Okay, so that's how you get finite generation for free, more or less. So this group is finitely generated. G. Finitely generated. So 1, it's not Hilbert-Schmidt stable. No, it's not the other one, permutation stable. And we started looking at these because we knew in advance that they were not permutation stable. So they did it for Abel's group, but this exact same proof shows that these are also not permutation stable. And then so that it is Hilbert-Schmidt stable. Okay, and I can't say much about the proof without leaving my low-level world. So now promoting this, we have an extra layer of non-commutativity. So to show that this is Hilbert-Schmidt stable, you really have to understand the characters. And to understand the characters, we had to borrow a lot of ideas from C-star algebra theory. Okay, so really this is a C-star algebra inspired proof. To really know how to control the characters without using C-star algebra theory. Over in that world, which is where I come from, we care very much about traces on algebras and what actions what actions keep unique traces. So if you have some sort of simple algebra which has a unique trace, we're curious, when you act on it, when do you remain unique trace? Okay, so we used a lot of these classic results to control these. To basically say, here are all of the traces, we'll just see why they work. To list all the traces. Okay, that's not true, but it's close enough to being true. All right, I think that was a first example of a amenable group that was Hilbert-Schmidt stable, but not p-stable, and I believe the converse is not known, right? Correct?
For amenable
groups, the converse is not known, but there are.
Oh, even non-amenable.
Non-amenable groups, yeah, that are p-stable but not Hilbert-Schmidt.
I don't think there's an example of a p-stable group which is not Hilbert-Schmidt stable.
I think there is, but I can't.
Open problem.
Either there is, or yeah, Thursday, that'll be our open. And then, oh yeah, for this one, we just embed this into a finally presented group that keeps the obstruction, right? So as long as, yeah, so this will happen. So we'll just embed it so that this remains normal in the finally presented group. So this is classic techniques to do this. So now, here, so I just used. So when I want to embed this into finally presented, I just reread Abel's paper, absorbed his arguments, and then wrote it down. That's my proof. But it's just this. So I had to go to 5, I think is. 2, and then you leave this one as an integer. So that's pretty sure works. So if you let these dots in here, I even stole his notation, that's what he does. And then m is now an integer. Okay, so I'll tell you where n is right here. So the 2 red dots are n. So red means your integers, let's say. Is n. And that one up there, that g, up there is the 2 red are these and that. So when they're red, it's n, and then the whole thing is g. And so the entire group is definitely not normal in it, but just the 2 red dots are normal in it. Because notice all of these things, they all commute with the red, so we're fine. And this is the only thing that doesn't. So this X on this, nilpotently like it did over there. And this is finally presented. So this, presented, and the obstruction persists. And I can say,
So what is the quotient here by n? I guess it's not amenable anymore, no?
no, evidence this. Oh no, wait, no, this is the wrong group. Sorry, this isn't right. It's definitely amenable. It's solvable. I forgot this.
Ah,
I need this to get finite presented. Sorry, so this is actually k and n are also integers. Yeah. So the quotient's definitely it's no problem. But I don't know how to get it explicitly. So before I get back to that, let me just point out one more thing. So since this is finally presented, these examples are also not locally Hilbert-Schmidt stable. So notice this group, G. So now that's G. So Eckhardt said something about this. I'll just say it in words. Instead of correcting everything to a true homomorphism, you just have to correct a finite set to a homomorphism, right? Yeah, so this also doesn't do that. So we get a stronger negation in that case as well. All right, now really finally, for the point, last question, finally. So I love to ask this question on Thursday, but it doesn't really have anything to do with stability, but I've made my talk, I can at least look back in my talk, which has something to do with stability in it, and this question is natural in the confines of my talk. All right, but I couldn't ask it on Thursday, so here we are. Do you know the answer to this? So suppose that, this is shameless, but I just want to know. So let's say gamma is finitely generated amenable. That's it? Okay. Can I find a residually finite amenable group that quotients onto gamma? Right? Can I find a residually finite amenable G? All right, so again, this has nothing to do with stability. I just thought in this room, maybe someone would know why it's false, why it's true. I feel like nobody knows this, and it's very hard, but maybe not. If even if you know that it's equivalent to some other hard problem, I'd be very happy to know. All right.
If it's locally embeddedly finite, then this is possible.
But what if it's not that? I mean, yeah, actually, locally embedded finite is fine. I can deal with those. For what I want this for, that's no problem. That's for all of them. So anyway, if you have any wild conjectures or goose chases, I'd be happy to take them. All right, 6 minutes early. I'm done. That's it.
Questions?
So what is the relation between this and?
Yeah, I have an idea on how to prove MFness for groups like gamma. And I want to know how general it is. So that's it.
Do you know for solvable?
No, if you know for solvable, that would be interesting also. I don't even know I know basically nothing or have any ideas on this. Yeah, so solvable, elementary, amenable, any sort of thing that is not just LEF.
I mean, for solvable, aren't free solvable groups are really fine, right? So that would. So I mean, every solvable group is the quotient of the free solvable group of the same rank, and that should be residually fine.
Okay, that's good to know. I'm already happy that I can.
If you replace those 1 over p with the p-adic integers, and in all the examples, and the groups would not be countable, but do you get similar results?
I really don't know. I have to admit I don't know what p-adic integers means. No, I don't know what p-adic integers are. I've heard that term and I've looked it up, but I forgot. I'll learn about it and answer your question.
All right,
The group is the theorem satisfy 1 and 2. Right? And it's
This one?
say obstruction persists.
This one, yeah, up here. So here, so what I mean by that is, all right,
No,
because,
but what are the properties of this
so this,
relation?
and this, and not Hilbert-Schmidt state. So I meant, yeah, so here's the normal subgroup. So it satisfies this thing where I embed it. That's it.
Do you think that it's possible that all subgroup separable amenable groups are Hilbert-Schmidt stable, for example? Like that this obstruction, like that all finitely generated subgroups.
Wait, okay, say that again.
That somehow this obstruction does not exist. You don't have a finite. You don't have like a normal subgroup for which the quotient is not real.
Oh, yeah, I don't know. That's the only way I can, yeah, this circle of ideas isn't going to work for anything because it all depends on that. Where I've got a non-residual finite quotient. Everything has to deal with that. So, I don't know.
For politically groups already, that's subgroup separable, and the question is
Yeah,
very
we don't-
interesting.
Yeah.
I mean, it's
Whether they're all Hilbert-Schmidt stable.
yeah, and it's likely that they're not. So
Yeah.
What was the subgroup separable and what?
Amenable, subgroup separable, finitely generated.
Probably all known examples are virtually polycyclic, I would guess. I'd be very surprised if there were other examples. So I see.
Same question.
with the operator to Hilbert-Schmidt non-stability, do you know if the things that witness that, if you could also show the sort of just operator norm thing with like a winding number argument or some other topological invariant?
What do you?
So like you have this thing that's multiplicative in the operator norm
Yeah.
and not perturbable in the Hilbert-Schmidt norm, which implies it's also not perturbable in the operator norm. Could you alternatively prove the operator norm thing with like the winding number argument or something like that?
I don't know.
Okay, fair enough. Any more questions? All right, let's thank him again.